Okay, now we'll match gamma L, which is 0.876 angle 61 degree. Okay, so first of all we have to mark angle 61 degree. So here it is 60, this one will be 62, minor division. So this one is 61 degree. Okay, so I mark this thing. Remember, I am not extending this one on the wavelength scale, because ultimately we have to transfer gamma L into YL. Now 0.876. So I will take that scale from this reading, and this turns out to be 0.8, 0.82, 84, 86, 87. So I marked 0.87 over here. So this is nothing but gamma L. Now go to diametrically opposite point and extend this on wavelength scale and mark YL. At the same time, I am extending this thing on unity circle so that this point is YL, this point is Y1. Now extending YL on a wavelength scale, I will get approximately 0.412467, around 417 lambda. And if I consider the upper point of intersection of VSWR and a unity circle, then I have to extend this thing on wavelength scale and this is 0.21 lambda. So if you move from YL to Y1 in anti-clockwise direction, you will get the distance of this stub. So that I am calculating. So the distance of the stub, considering solution 1, you can write upper point on unity circle. For designing, you will get distance as 0.417 minus 0.210 lambda, and that turns out to be 0.207 lambda. So this is the distance of the stub. Now for the same point, if we have to calculate the length of the stub, open circuited stub, so we have to extend this point on wavelength scale, along the arc. So I extended this point along the arc, and now this turns out to be 0.206 lambda. Be careful, this is not 0.26 lambda, this is 0.202, 204 and 206 lambda. 0.26 lambda will be over here. Students often make mistake over here, so it has to be 0.206 lambda. So the length of the open circuited stub, so as we know, this is nothing but the open circuited point in Y Smith chart. So we'll measure the distance from this one up to this one, and the length of the stubs, open circuited stubs, turns out to be 0.206 lambda. Now if you consider the lower point on unity circle for the matching, then Y2 is over here, and it is quite evident that the distance of the stub will get reduced. So that I am calculating. So you extend Y2 point on wavelength scale, and here it is 0.292 lambda. So the distance of the stub will be 0.417 lambda minus 0.292 lambda, and this turns out to be 0.125 lambda. Yes, the distance turns out to be 0.125. Distance turns out to be 0.125 lambda. Now we have to calculate the length of the stub. So I will extend this point along the arc. and it comes over here. So if I measure or if I extend this thing, then this is nothing but 0.297 lambda. So the length of the stub will be 0.297 lambda. So you can show any one solution on the circuit diagram, and if your diagram will be like this. So this is your transistor, this point is gamma S, this point is gamma L, and we have designed the open circuited single stub matching networks to match gamma S to 50 ohm and as well as gamma L to this 50 ohm. So the length of this stub gamma S we have calculated in the last lecture, and it turns out to be 0.124 lambda, while the length of the stub turns out to be 0.200 lambda, considering upper point on the Smith chart. Now for the gamma L we have calculated, we have these two solutions. So for this solution I will represent in our diagram. So this turns out to be, distance will be 0.207 lambda and this length will be 0.206 lambda. This is the length of the stub, which is 0.206 lambda. Now even one can calculate the actual length, because the frequency was mentioned in the question, it was 4 gigahertz. So one can express these lengths in terms of millimeter. So frequency was 4 gigahertz. So one can calculate lambda easily. There is a simple formula to calculate lambda. So lambda is nothing but 30 by f in gigahertz, and you will get lambda in centimeter. So it is 30 by 4. Simply 4 gigahertz, you just substitute 4, so that will be 7.5 centimeter. So this length will be, you can easily calculate in centimeter. So we'll calculate .5. So we'll type 7.5, which is nothing but lambda into alpha A, and I will calculate for the various values of A. So the first one is 0.2, so it turns out to be 1.5 centimeter. Then for 0.124 lambda, it turns out to be 0.93 centimeter. For this one, .5525 centimeter, and for 0.206 lambda, it turns out to be 1.545 centimeter. Now the last part of the designing is we have to calculate the overall gain, transducer gain. So the overall transducer gain consists of 3 parts: the gain from the source side, gain from the transistor itself, and the gain from the load side. So these are the corresponding formula. So we'll calculate this thing one by one. So this one will be 1 upon 1 minus, and in the earlier lecture we have seen that the gamma S is 0.871 angle 123.4 degree. So I will use mod of gamma S as 0.871. I can calculate the gain as 4.143. Now I have to convert this into decibel. So this is equal to 10 log of this one. So it turns out to be 6.17 decibel. H21 square. So H21 was mentioned as 2.6. So this is 2.6 square. So that is 6.76, and now I have to convert this into decibel. So log of the answer multiplied by 10. So it turns out to be nearly about 8.3 decibel. And the value of GL. So gamma L 1 upon minus 1 minus 0.876 square divided by mod of 1 minus, and H22 was 0.73, angle minus 54, and gamma L 0.876, angle 61. So this will calculate so 1 minus 0.876 square divided by mod of 1 minus 0.73, angle minus 54, into 0.876, angle 61. And mod square is there, so this is equal to 1.66. so in decibel it turns out to be 2.22 decibel. So overall gain GT max will be GS in decibel plus G0 plus GL in decibel. So it is nothing but addition of these three values, 6.17, 8.3 and 2.22. So plus 8.3 plus 6.17. So it turns out to be 16.69 decibel. So that completes the numerical on the amplifier design for maximum gain when the transistor is not unilateral but it is bilateral, because S12 is not a 0, so this indicates it is a bilateral transistor. And we have designed the matching sections using single stubs. So in the next lecture we'll see one more numerical on designing of maximum gain. Thank you.